A Petersen coil is an intelligent protection and stabilization element in medium voltage networks and, in some cases, also in high voltage networks. It ensures that single pole ground faults can be controlled safely and without immediate shutdown. This makes it an indispensable component of modern power supply systems. The Petersen coil is an inductive coil that is connected to the neutral point of the transformer. In a three-phase AC network, capacitive currents flow between conductors and earth. If a ground fault occurs, a capacitive fault current flows through the fault location. This can be dangerously high. In the event of a fault, the Petersen coil generates an inductive current that is opposite to the capacitive fault current, and in the ideal case, compensates for it at the fault location. A small pure cable network with 300 ampere earth fault current in the fault case is to be simulated. This is 3 times the capacitive load current of the cable. The full earth fault current only occurs in the event of a fault. During normal operation, there is a low neutral point voltage at the Petersen, which means that the nominal current of the Petersen does not flow, but a much lower current. In the event of a fault, with a full earth fault, the full phase voltage is applied to the Petersen, and the nominal current of 300 ampere flows. In this example, unless otherwise specified, the transformer is assumed first to be without load. The time at which the error occurs is stated at 205 milliseconds. With the text parameter of the voltage source, the steady state is quickly reached. A star delta 5 transformer was used for the simulation. The transformer data can be viewed in the here you look for XKOS. This is the sum of primary and secondary impedance of the transformer related to the primary side. Therefore, the primary side A impedance is about 30 ohm. Now about the adjustment of the Petersen at no fault condition. We now load the file Petersen without fault. We see the 110 kilovolts voltage source with isolated star point, a reactive metering device, a net impedance, 3 line to earth capacitances of the cable, a small line series impedance, and a YD5 transformer. The earth fault switcher is set to a very high time value of 1,000 seconds, and so it is deactivated. The load is initially 0. The cable, a 10-kilometer oil cable with cross-section of 1,000 square millimeter, has a line to earth capacitance of 5,012 nanofarad per phase. This corresponds to impedance of 635.1 ohm. The charging current is 100 ampere RMS. Since the earth current in the fault case is the triple of the charging current, the impedance of the Petersen coil is 300 ampere RMS, and the inductance of the Petersen is not 0.674 Henry. At the network element Petersen, you can directly input nominal voltage and nominal current, in this case 110 kilovolts and 300 ampere. Note, 300 ampere is the first initial guess for the Petersen current. There is no inductive coupling between phases modeled in the series impedances of the line because our focus is the operation of the Petersen. With coupling, the earth fault current at the beginning of the fault would be a bit smaller than without coupling, but the same at the steady state. The transformer is assumed linear, and the magnetic resistance of the oil tank is assumed first very high at 1E20. This means no oil or tank considered. The transformer core is a 3-leg core. Now to the displacement voltage of the transformer star point seen in the transient analysis. In the faultless case, there is a displacement voltage at the star point of the transformer and therefore also at the Petersen coil. This displacement voltage is in our case 1.2 kilovolt peak and much smaller than the nominal voltage. The voltage depends on the asymmetry of the line to earth capacities, in our case CE plus CE1 on phase 1 and CE at phase 2 and phase 3. The more asymmetric the network, the higher the displacement voltage. I start now the transient simulation. As can be seen, the displacement voltage builds up slowly and oscillates at a frequency of approximately 1.2 Hz. This indicates that the resonant circuit is not yet optimally tuned because this frequency does not yet correspond exactly to the working frequency of 50 Hz. The frequency can be easily seen in the waveform viewer if you span a zoom window between two maxima of a waveform. The frequency is then written to the status line below at left side. Now to the displacement voltage seen in the alternating current analysis. For the alternating current analysis of the circuit, the voltage source has to be changed to an alternating current source. The transient analysis line is changed to an analysis line. This is all. You see after simulation that the voltage across the Petersen is in the resonant case approx 4 kVRMS. This is higher as the 1.2 kilovolt peak of the transient analysis. Note, to set up the y-axis of the waveform viewer for magnitude values, right-click on the y-axis and set option Bode and option Linear to see the magnitude and phase values. In the optimal case, the displacement voltage has its maxima. One sees that the maximum voltage level is at 48.8 Hz. This explains the difference frequency of the tran analysis with 1.2 Hz. At 50 Hz, the voltage level is at 0.8 kilovolt RMS. This is a peak value of about 1.2 kilovolt, what we have seen above in the tran analysis. Also, the AC analysis shows that the resonant circuit is not optimally adjusted. To compute the resonant frequency by hand, see the following formulas. We have seen that, although arithmetical correct, the resonant circuit with cable capacitances and Petersen coil is not optimally compensated. The reason is in reduction of the star point voltage due to the internal primary impedance of the transformer. The impedance is at 30.25 ohm. It is relatively high, and so the nominal values of the Petersen with nominal current of 300 ampere cannot be reached. We try to adjust the Petersen to 315 ampere and restart the simulation. You can see now the displacement voltage has its maxima at 50 Hz. This is the peak of the resonant curve. Now we set the initially chosen 1E20 value of the magnetic resistance for the oil tank to a more reasonable value like 1E6. I think reasonable values for the oil tank resistance are 10 till 100 times of the leakage reactance of the transformer, which is about 0.1 Henry. We set the oil tank reactance to 1 Henry. After setting the oil tank resistance to 1E6, we restart the simulation. Now we see that the resonant point is again lower than 50 Hz. The resonant point is now about 49 Hz, so we have to increase the Petersen value again. We choose 328 ampere. We restart the simulation. Now the resonant point is again at about 50 Hz. To see why the inner resistance is now higher, we see the file Petersen with fault hierarchical model tran. After starting the simulation with R Kessel equals 1E6, we see that the current of the Petersen is about 330 ampere. We see that now high currents flow now as circular current in the secondary windings of the transformer. This is the reason about the doubling the voltage drop of the transformer. Note, we have seen above that the sum of all cable capacitances is not the sum of all Petersen values because of inner resistances of the transformer. We have to add about 10% for Petersen current value to compensate the internal transformer voltage drop. Now from the practice, the automatic Petersen is normally working a little bit undercompensated, a uncompensated current, e.g. 6 ampere capacitive. Additionally, the Petersen automatic is switched off in the fault case because the optimal value of the Petersen is yet set at no fault condition. Now to Petersen at fault condition. Now we have tuned our Petersen optimally, and we show how the Petersen coil work on fault condition. We start now again with a transient simulation to show the transients of the currents after begin of shorting phase 1. We see now the shorting time at 0.205 seconds at voltage maximum. The initial current at the fault position is about 4.3 kiloampere and goes to about 4.6 ampere peak after a long time. If the starting time point is changed to 0.2 seconds at voltage 0 for phase 1, the current is much smaller with a peak of 800 ampere and about 4.6 ampere after a long time. Now we look again to the transients for the shorting time point of 2.05 seconds at voltage maximum in phase 1. We zoom into the starting current and see that the currents are highly nonlinear. One frequency of the current is about kilohertz. Another frequency is about 250 hertz. You can measure this again directly in the waveform viewer and the status line. You can also measure this by the FFT feature of LTSpice. You can see that in the fault case there appear some frequencies. The highest frequency is on the shorted cable capacitance of phase 1. This is about 1.25 kilohertz. The currents of the other capacitances and the phase voltages have a frequency of 250 hertz. We now explain the doubling of the reactive power at the beginning of the fault. This is done best without Petersen and with isolated star point in the file. Petersen with fault isolated star point tran or Petersen with fault isolated star point AC. Due to recharging, two capacitances are now at line-to-line voltage, and the third capacitance is discharging by the fault. The source current rises to the double value. Note, at the Y-delta transformation, the power will be 3 times higher. Since one phase fault is shorted, the capacitance is there zeroed. Therefore, the power is only 2 times high. One part of this doubled capacitive power is after swing in compensated with the Petersen coil, and the single capacitive power remains like at the state before the fault. Doubling the capacitive power cannot be observed directly at the beginning of the simulation because it is overlaid with the high-frequency transient responses. Before the fault of phase 1, the capacitive reactive power is about minus 6.3 megaVAR per phase, minus 19 megaVAR sum. At the beginning of the fault, the power rises due to recharging at higher frequencies. The reactive power of phase 2 and 3 reached the long-time value of APR minus 20 megaVAR. The sum after swing in is approximately 40 megaVAR and so more than doubled as at starting time. Why more than doubled? Because of the now higher voltage level, 2.5 kilovolt. Now we add additional load to the transformer. Since the Petersen current have to flow through the transformer windings, the transformer is additionally loaded. In our example, the Petersen current is 108 per phase and the nominal current of the trafo is about 190A at the primary side. Since the current is a vectorial sum and the Petersen current is purely inductive, there remains relative much active current. The reactive part of the load is about 1/5 of the active power. So in our example, approximately 75% of the load remains. To the comparison of unloaded with loaded transformer. If you change the load from 20E6 to 40E6, you can see that the phase voltages and the star point voltage drops a little. Since also the voltage at the cable capacitances drops, there is no effect to the tuning of the Petersen. We now see a 10 kV compensated network with external star point builder transformer. You see a Petersen in a medium voltage network. Due to the star point builder, a YD transformer can establish a star point at the secondary side for connecting a Petersen coil. Some words to Petersen on a YY transformer with 3-leg core. Since the YY transformer has no low ohmic return path for flux in the core of the transformer, the flux have to go through tank and oil. This is not the goal. Therefore, the star point should only be loaded by maximum of 10% of the transformer nominal current. If the YY transformer has a 5-leg core, the star point cannot deliver any current if the second star point is isolated. This is because the low reluctance of the outer legs short the magnetic core for same-phased fluxes. If the second star point is also connected, current can flow from one into the other star points, but current should not be exchanged between the two star points. In short, the two star points of a 5-leg YY transformer should be isolated. See file. Now to Petersen on a YY transformer with 5-leg core with compensating third winding. The transformer can deliver full current at the star point. There is also no current transfer from one to the other star point. Now we are at the end of the Petersen example. I hoped you had fun with this short workshop. Good luck simulating